So where's the clicker gone? Someone's stolen it. So I'm Darren Soothill. I'm from Croit. Croit provides a wrapper around a Ceph deployment. And we'll talk a little bit more about that shortly. But the conversation about this was making the right hardware choices. What we see more often than not is people who've made the wrong hardware choices end up having problems, whether that be data loss, performance, things like that. That's what we see time and time again. A little bit about Croit. The big one really I wanted to pull out here, we've got over 400 customers. Those 400 customers are relying on us for support. So we get to see when they have problems. So we get a very good idea of when things are going wrong. So that's a bit about where Croit is. Yeah, 25 years of storage pre-sales. That's where I've come from. 8 years of doing pre-sales for Ceph. First installation of Ceph on an ARM-based server. That was going away to a hidden room in ARM's labs with a box that had no labels on it, with a special kernel build to enable it. So see many configurations over the time. Some of our fastest clusters that customers have, 90 servers, 720 OSDs. So we're doing S3 on top of that, 50 petabyte clusters. We've got CephFS with billions of files, and also doing IO 500 submissions with Ceph on ARM. That was when Ampere first came out with their processors, so they got us to do that for them. So interesting set of things over time. Why this presentation? Lots of customers get the hardware choices wrong. The number of times we see customers come along, I've not put NVMEs in, I don't need them, they've got least to poor performance. We get other conversations that happen where people are going, I'm only writing 2 copies of my data. Yeah, exactly, shaking your head there. But they've been told that by a consultant somewhere. And they were there, all right, it was all flash. They've looked at Micron's white papers that they did, which were performance on 2 copies. That's the thing there. So some of the Ceph hardware vendors are selling bad configs as well. So one of the common ones we see there is people wrapping round multiple parts onto the same set of 4 nodes. So they'll do 4+2 erasure coding and wrap that round across 4 nodes. Those are the customers where we see data loss. The guy's writing 2 copies. Well, it's all right if you want new data, maybe. But what I was going to say here is not the only way to do things. This is what we generally see for our type of customers and the workload that they are typically putting on there. So you may not agree with some of the things, may have different discussions. Hey, that's a long thing. So number of nodes. You should always have 1 more node than your failure domain. So, replica 3, minimum of 4 nodes. We get some people try to push things a bit on that. Okay. Erasure coding. If you're doing 5+3, so you've got 8 pieces of data, you need 9 nodes to spread it across. If you haven't got enough nodes, you end up putting 2 pieces onto a single node. In fact, if that node fails at all, you've now lost multiple parts potentially. We see these types of things happening. When we see customers break these rules, very often we get data loss. 4+2 erasure coding on 4 nodes. I can think of 3 or 4 customers who've come to us who've been sold that as a hardware configuration by a hardware vendor. And it comes to us and they're going, help. And we can't always get the data back because there's not enough pieces left. So that's one. Replica 2, the standard one we see again. We see that time and time again where people are trying to save money or they've been told it's good enough or something like that. And really, only if you don't care about your data. It's fine if you're just using it for scratch space. Fine if you're just using it to ingest somewhere that the data's going to go and you've still got an original copy of the data. But you don't want to be storing your data on there as your long-term repository. But some people seem to do that. RocksDB/wall on NVMe. If we don't do that, we get extended recovery times. So the RocksDB database is not particularly efficient. It does a lot of I/O. If you've got that on a hard disk, it takes potentially hours. Any maintenance such as compaction takes an extended amount of time if it's only on hard disk. We actually see that same problem happening if you start to get spillover. So if your RocksDB database can't fit on the amount of NVMe space you've got, RocksDB will automatically spill it onto a hard disk. That's fine if you're not going to access that data is going to be there and really not done. The people who really get caught out of that are the people who are using it as a backup destination. Because guess what happens? Every so often they come around and delete the old data which is the old backups which have aged out. Suddenly they start getting into big performance problems with doing that. Can slow your cluster down considerably as well, because now all writes can only go to the hard disk. If you put an NVMe in there, small writes will go to the NVMe, your RocksDB and Wall are on the NVMe, so you end up with a better performing cluster. The amount of objects affects the amount of NVMe needed. And this is an awkward one, and it depends on what percentage you think you need and what your number of objects. You know, if you're going to fill a cluster up with 2K objects, you're going to need a lot more NVMe for doing this. If you're going to have a cluster that's got 50, 60 RBD devices on there, you don't need as much NVMe storage. So it's a bit of a random number, but that's where we are. You know, normally a 1 to 12 ratio of NVMe to hard disks. So for every 12 hard disks, you need an NVMe drive. The upstream recommendation is 1 to 4%. Typically for most of our customers, we're seeing more of a 1% side of that. It varies a little bit depending on the workload, what the workload is, but where they've got a lot of large objects, then you're definitely down at the lower end of that. There's some changes being done with newer versions, such as compression of the RocksDB database. So that's actually potentially going to change this percentage depending on what you're doing, because it's going to take up less space. So fortunately, one of the people who works for us is Igor Fedotov, who does all the OSD code. So we're very aware of what's going on there. And, you know, we've applied some of these changes for the compression to customers who've started to see spillover, and it's saved some of them the need to buy more capacity in terms of NVMe's. The big drive tray chassis. We see this one come up again and again because people go, hey, we'll get one of these, we can get 80, 90, 100 drives in the chassis. That's great, but A, is your rack able to cope with it? Because these things are about 1 meter deep. And then you've got to put your cable management arms on the back of it as well. So the first thing is, if you're going to use one of these, you probably need a special rack. And you also get a lot of heat in a small amount of space in a data center. Drives are replaced by top loading. So you've got to pull this thing out, get your drive, pull it out, put another drive back in. That's fine when it's this height on a rack. What are you going to do when it's up here? And, you know, there's all sorts of health and safety issues and things like that. But, you know, generally, given a choice, I would never go near those. But I accept that some customers see that as a way to solve certain things. We have customers who've moved away from this type of thing. They have SAS cables. Every time you pull the tray out, push it back in, you're now putting stress on those SAS cables. You know, so they've moved away from that because of the amount of SAS cable failures we're getting. Okay, it doesn't cause an outage because you'll have 2 cables connected, but they've certainly had problems with that. So generally, I'd stay away from these big things unless you've got some silly amount. If you've got 100 drives in there at 24 terabyte drives, you've got 2.5 petabytes in a single tray. That's a lot of capacity in there to be managing. Things like you need a lot of CPU cores to run that lot because you've now got a lot of drives in there. Now, yes, you can split those up into multiple pieces, but then it starts getting to the point of, is it actually any more efficient than moving to a smaller chassis? The next one that we see is a top loading chassis. So these have 50, 60 drives in that you load from the top. The problems with these is there's usually not many NVMe slots in the actual chassis to do things because they've taken all the space up with hard disks. So your problem you get then is I can't get to my 1 to 12 ratio. And if I need to get to a 1 to 12 ratio for NVMe's to hard disks, you know, if you've got 60 drives in there, you're going to need 5 NVMe's. There's not enough slots in those chassis to put 5 NVMe's in. So you can't, and there's no extra slots for MDS/S3 metadata. That's really another key bit that we see as well is people needing to spread that around. So limited PCI slots. Again, typically with these ones, you have to pull the whole chassis out. Some of them have done other things where you pull things out from the front. But again, there's a big challenge there. The most common config that we do is some form of 2U24 type of configuration. So you've got 2 U's, you've got a set of drives at the front, a set of drives in the middle. This part slides forward, you can replace these drives, or in this particular chassis, it pulls forward and you lift up. And that is a nice place to be in terms of CPUs. You're not having to buy higher end CPUs. Easy to service, good mix of capacity density. We're getting 24 drives in 2U. So in 4U, we've got 48 drives. We're nearly at the capacity of those top loading trays straight away. The big advantage, though, is you can actually put NVMEs in the back. So normally with these, we'll have 2 NVMEs in the back as standard. If we're doing metadata or we're doing S3, there's usually space to add another couple of NVMEs in the back as well. So now you've got the same chassis doing everything. The other big change here, with modern CPUs now we can get down to single socket systems. So we get rid of all the NUMA bus issues of traffic going across NUMA buses. But that's a big choice there and brings the cost down. So, lower cost of motherboard, and you don't need lots of PCIe lanes for hard disk configs. You put in a SAS controller in there, or maybe 2. You don't need that much PCIe lanes to do that. All NVMe configuration is a bit of a different story because you're needing to get lots of PCIe lanes to get to all of the drives that are in there. So that's sort of, I'd say, probably 90% of the systems that we are involved in speccing up with customers do some form of that type of chassis. And there's, depending on which vendor the customer prefers, they, it may have slightly more, slightly less, but that's typically what we sort of see there. Networking. This is another one we see a lot of customers with challenges, and then they go, oh yes, we're only going to be archiving at this rate, or we're going to be writing at this rate. What they forget is that recovery is actually the time when the network usually generates most traffic. So, now typically we go minimum of 2 by 25 gig ports. There's no real price difference between 10 and 25 gig ports. Most core networks have moved to either 25 gig networking or they've moved to 100 gig networking. With 100 gig networking, you can break that out into 4 25 gig ports as well anyway. So number of drives increase in network requirements, also the type of drives as well. For all NVMe, we're now looking at 2 by 100 gig as a minimum point for that type of configuration. And we don't tend to separate front-end and back-end networks on physical ports. We may put different VLANs in if a customer wants to do that, but we tend to not see the need to do that as much now as it used to be when you only had 10 gig connections, and with 10 gig connections you can max out the actual throughput that was going through the system. Drive types, the bane of my life. So, in this day and age, why would anyone ever put SATA drives into a Ceph cluster? There's a whole raft of technical reasons why they're not that great, and that improves performance, the ability for them to handle multiple command queuing in a better way. So that's sort of SATA drives. M.2 drives, we'll come into those a bit more in a minute. SAS SATA SSDs. There's no price difference between a SAS SATA SSD and an NVMe drive now. So why would you hamper yourself to 500-ish megabytes a second when you could have gigabytes a second? You can have massive numbers of IOPS here compared to these drives up here. For hard disks, I would always be specifying SAS because that gives the better ability for recovery, management of the drives, things like that. And then obviously NVMe, and we'll talk a bit more about NVMe types shortly. Hard disks. Do not, under anything, use SMR drives. They will kill performance. They are horrendous. Their write performance is horrendous. You just don't want to go near those drives at all at the moment. Consider your workload. Some drives you can get use flash or other methods to accelerate writes. If you've got a heavy write-intensive workload, then maybe if you've got a drive that can sustain 1,000 4K IOPS for writes, that maybe is a better fit for what you're trying to do. So that's something to consider there. These flash to accelerate writes don't help with reads. So again, what's your workload? Is it a heavy write intense workload? Are we doing lots of writes? Are they reading a little bit? So a backup server, an archive server, those types of servers could be a use case of that, which could actually accelerate the overall performance. If you have a small cluster but need better performance, and I'm assuming you're going hard disk at this point, we've actually had quite a bit of success with the dual actuator drives. So what that is a drive that you put in, and it appears as 2 drives because it's got 2 heads on it. So it's got 2 actuators moving backwards and forwards. So you get twice the performance for the same number of drive slots. So they do those in 18 terabyte drives. They appear as 2 9 terabyte drives. So now you've got to think about, you've got to do double the CPU, double the memory as well, because they are effectively 2 OSDs, even though they've only taken up 1 slot. So with a 24 drive chassis, you effectively end up with 48 drives. We're seeing a bit more of a use for these because when people are looking to replace capacity, or replace drives, replace the hardware, they may have bought a system that is built on 6 terabyte drives, 8 terabyte drives. Those drives I don't think 6s are available. I think 8s have gone end of life, or are going end of life for a lot of people. So that may be a case where you can keep the effective spindle count up for the customers and what they're trying to do. So it's just something to consider, because we are seeing quite a lot of Ceph clusters coming around to, hey, we're reaching the end of life, or we want to replace it, or the supplier that supplied the original cluster is no longer doing that anymore, and they're going, what can we replace it with? We can't afford to go all flash, so they're looking for something in that middle type of ground. M.2 drives. They're the only type of drive that we see wearing out. And we get people trying to use them for MONs, and if they're not big enough, the amount of writes the MONs can generate will wear these things out in 14 to 15 months is what we've seen with some clusters. So I really wouldn't do those. If you're using MONs, they need to be at least 1 terabyte. So people tend to go, hey, we'll grab an M.2 drive, we can get this 480 gig one, stick it in the server, we'll use that for the MONs, because the MONs don't need much disk space. The problem is the amount of data that can be written to them wears them out, and wears them out fast. So the other problem is usually the M.2 drives are shoved somewhere down on the motherboard or in some weird place, so they start to overheat as well. Bearing in mind we're doing a lot of writes to them if they're a MON, so really just stay away from them. As I say, we've got numerous customers who've done that type of thing, put those drives in, and 14, 15 months, the drives start alerting that they've exceeded their, what's the wording it uses? Exceeded their durability or something daft like that. Basically, they've had too much data written to them, so A, they're outside the warranty of the manufacturer, and B, they start failing. NVMe devices. Not all NVMe devices are created equal. And I'm not talking here about consumer ones, I'm talking about enterprise class devices. And I'm talking about certain vendors who provide those. Their drives are not a good fit for a Ceph type of environment. Must have power loss protection. So power loss protection allows the drive to actually take writes in and have not written them down to flash, so you actually get a better response time for them because they'll sit in that area. TLC drives are not QLC drives. TLC drives are 3-level cells. I am seeing some people talking about using QLC drives now. So these are the ones that are like 30 terabytes, 60 terabytes in a single drive. If you're going to do that, where's your RocksDB and your wall going to go? Because these drives do not have a very high write performance. So we're seeing people having to add a TLC drive. When you start adding up the prices of doing that and the extra slots that are needed to do that, it becomes a bit challenging, shall we say. It's not always financially the right place to go. Some drives exhibit very variable latency. If you want to see some graphs of that, the Ceph Days New York, one of the guys there had some graphs of exactly this sort of problem that we've seen. We had a customer, they had a set of drives from one vendor. They came along and bought another set of drives. They worked perfectly fine to start with. Those drives were working perfectly fine, everything was okay. Then the drives start to get a bit older and the cluster starts to get a bit more full. So there's less free space for the drives to do their housekeeping. So when they deployed a second set of drives, they suddenly started getting slow ops and latency problems. We started digging into this and found that vendor M's drives were very bad, and we could tell them which drives were from vendor M and which drives were from, I think it was vendor S was the other one. And we could tell them which drives were which just by looking at the latency that we're seeing. So be careful about these. We're seeing a lot of this problem and it's cropping up a lot. So yes. Memory. Uh, Memory is relatively cheap, so we tend to go for 8 gigs per OSD device. So I say per OSD device. If you've got Mac 2 drives, which have got dual actuators, you need twice that. We also see some of the hardware suppliers putting memory in weird configurations, so they don't necessarily use all the memory buses that are on the processors. It's always better to have too much than not enough, because things like the out-of-memory killer will come, out-of-memory processors will come around and kill OSDs, and suddenly you can find that OSDs are getting restarted. They restart so fast you don't know that that's actually happening. If you're co-locating gateways, you will need more RAM, because those gateways themselves can consume a lot of RAM. And again, depending on the workload, you may not see all of that RAM being used during normal operation. It's when recovery starts, which is when we see most RAM being used. The Ceph is a little bit challenged with managing the amount of memory, shall we just put it that way. So you will see memory start to balloon above what you've actually done here in certain cases. So typically with a 24 drive chassis, we're going to put 256 gigs of RAM in, because that's what balances the memory across all of the processor buses, and that's the sort of space there. If you're doing that with 24 drives, then you've got plenty of memory to run some gateways on there as well. CPU type. We've got Intel, we've got AMD, and we've got ARM. They're all capable of running Ceph. We have customers who are running Ceph on all of those processor types. All good for general purpose hard disk clusters. So that's where we need to be careful when we get to doing high throughput. And this is some things that we found. We were doing some work on an NVMe over Fabric gateway. And the gateway, dual gateways, load balance, we were driving 1 million IOPS through it at sub-millisecond latency. Customer tried to reproduce this and only got 250,000 IOPS. We went through looking for all the differences between them. And eventually, the only difference we found was the CPU type of the gateways. They swapped the gateway out for an Intel-powered one rather than an AMD-powered one, a much older gen CPU, and suddenly they were able to get up to the sort of performance numbers that we'd got in our lab. So it's something we need to do a bit more work on, but definitely the AMD chiplet design seems to be adding latency to IOs. It's not much latency, it's a small amount, but when you're driving 1 million IOPS through this, then suddenly this starts to become apparent. So the extra NUMA buses and the fact you've got to move data from the processor core onto the PCIe processor to get data out is when these things start to appear. As I say, bearing in mind what we were driving up here originally. And so this is something we're a bit concerned about, shall we say, on that side of things. Number of cores. Number of cores used to be a simple thing that you put 1 2 gigahertz core in per OSD. And if it was NVMe, you might double that, you might quadruple that, depending on what you're trying to do. The challenge here is that the Ceph documentation now is talking about number of clock cycles per core, per OSD for the IOPS you need. How many customers know what the IOPS they're going to want to drive out of their OSDs are at the time at which they put the cluster in? They don't. We really need to be going back to, this is what we still work on. 1 by 2 gigahertz core per hard disk for OSDs, potentially 4 for that if it's NVMe's. It's a difficult one, and I think the whole Ceph community is making this more complicated, because I kept seeing on a few slides earlier on they were talking about, IOPS. They don't definitely define what an IOP is. That's a good question. Is an IOP 4K? Is it an open? Is it a close? Is it a 1 meg? Those are all IOPS. So when people start talking about needing this for number of IOPS, it doesn't make sense always, and customers don't know this and can't size it in most systems. Unless you're replacing an already running system, you've got no way of measuring what IOPS are going to generate. They don't know what IOPS are going to generate, and they may not know what their users are actually going to be doing on the systems. If you're putting in clusters with dedicated MDS servers, then we'll always go for clock speed over cores, because the MDS process is still quite single-threaded in some of the things it does, so trying to get things done as fast as possible is really important with doing that. So that's sort of that side of things. One of the things we have seen as something that we've got some of our customers wanting better S3 performance doing, traditional setup, you'd have your app that talks S3, S3 goes to a load balancer, goes out to Radus Gateway, goes out to Ceph. There's obviously potentially a couple of network hops there, you can co-locate some of those things. Typically they're all on separate hardware. They've got a load balancer that wants to be protecting against multiple Ceph gateways. So we have one customer that was doing very high throughput stuff on 90 node, 720 OSD cluster. What they've done is to put the Radus gateway and run the Radus gateway on the same node as their application. So now the application talks to the Radus gateway. We don't need a load balancer because it's the only one that's there. And then that Radus gateway talks straight out to Ceph. So Radus gateway runs on the application machine, great, reduces network latency in doing that first request, reduces network latency. Downside is Radus gateway restarts need to be coordinated with the client application. We can't just go and restart the Radus gateway here because the client application, unless it's designed to work around it, is going to suddenly say, I can't get answers back. Most customers, if they've got a distributed one, can control when this app restarts, so they can drain stuff going to this particular application server, restart the Radus gateways or restart the node. But that's the challenge there with doing that. But I think certainly we're seeing more and more of this type of moving the gateway piece closer to the actual application server rather than having it sat somewhere in the middle of a network and you've got multiple hops to get to it. Yes, it does have some challenges that you need to be aware of, but those are the sorts of things that we are seeing people doing now. Questions at that point?
Yeah, great talk. You mentioned vendor M and vendor S. If you had to recommend, or if you're building your own server, what letter vendor would you go for?
So I would be looking at Kioxia, Solidigm, which used to be Intel, by the way, those types of vendors, not the other S. Oh. In order of preference, vendor M would be the bottom of the pile, and our guys, as soon as they see this latency problems, the support guys, they start looking at that straight away. I know there's some work being done in upstream Ceph to try and push more unmaps or trims down to the actual drives, because those particular drives need they don't have a lot of over provisioning, and so that causes performance problems for them. So that's sort of the challenge that's happening there.
Okay, thank you.
And I think just in front of you,
So about the AMD versus Intel, is it just the processor, or you basically change server because the architecture for the PCI?
Well, obviously we had to change. The whole server was changed, obviously, but it was the same NICs and things like that, so everything else was the same on it. So
AMD, I think the difference, Intel has a PCI switch and AMD doesn't.
Yeah, but AMD's got to do an extra mem copy to get from the processor complex to the I/O, the chiplet that does the I/O, and that's what we believe is causing a lot of the problems. Trying to get answers out of AMD on that is a bit problematic at the moment, but yes.
Thank you.
Thanks. So you said that moving your Redis gateways to the client side is giving you better latency.
Yes.
So do you run several zones then for those different clients, or how do you?
It's just every client machine is running its own Radus gateway, which talks back to Ceph at that point. The application, so a bit more of a background behind that. What they're actually doing is simulations in their application. So they pull the data out with S3, write it to a Radus block device, and there's multiple jobs running in the cluster at the same time, and then present the Radus block device out to the 4,000 compute nodes. So they now see a full inflated file, and they access the block device as though it was a local file and read and process from that. They're doing large files. They're doing big things to do that. That's not going to work if you've got millions of small files. Where you've got these bigger files in the way they're working, that's what satisfies their requirement.
So they don't need to coordinate between the different Redis gateways, because this I would expect to have a certain latency influence, I would say, just running within the same zone.
The Radis gateways are actually the limiting factor more than anything else. They're just not able to drive enough traffic through the Radis gateways compared to the performance they've got of the back-end Ceph cluster. You've got 700 NVMe's or 700 plus NVMe's sat there. They're basically not doing much work when they pull that out. So they're not seeing that as a problem, and having multiple Radis gateways is something we're seeing. It's more down to Radis gateways being inefficient than anything else. We've got another customer we're working with. We tried running the Radis gateways out on the actual OSD servers, and they were just chewing up CPU time. And it basically happened when you over queued the actual Radis gateways. So we had a job running that was transferring 64 meg chunks. And when we overqueued the Radis gateway with too many jobs, the CPU went through the roof, the performance didn't increase. When we brought the number of jobs back down, suddenly we saw the CPU usage decreasing, but the performance at the client side was still the same. So that's something in Radis gateway, haven't got to the bottom of that yet, that's causing problems there, but that's another one that we're going to look at, moving the Radis gateways out, because they're going to have a relatively small number of OSD servers and potentially a much larger number of application servers at the front end. So that's what they're looking to do there. And that's about tiering from these front end application servers to the back end Ceph stuff, both for reads and writes. So they're shifting a load of data back to write it, and then going to pull it back to read it as well.
So that means also that the major workload is read.
So the major workload?
The major workload is large read.
Yes.
Or just downloads.
Yeah, I mean we
get.
Yeah. So yes, that's what's happening there. In actual fact, they're doing. We need to understand a bit more about the workload, but they're potentially doing sub-gets out to the bigger file as well. So again, more gateways is going to be better for doing that rather than fewer gateways.
Cool. Thanks.
Just going back to the AMD versus Intel thing, I was wondering if you had any experience or were anticipating any issues with the Meteor Lake chips, which I think are doing a similar chiplet-based design.
Haven't got round to those yet. I know they're coming, and I know they're changing things, but I believe they are changing things in a slightly different way. So it's not supposed to be hit in the same way, but I haven't had one in my hands to try that with yet.
Okay. Another question. I was just curious about the first Ceph installed on the ARM machine you mentioned earlier.
Yes.
I was just wondering how you know that was the first one. Did you have to do some development work?
Yes, we had to. So basically with an ARM processor, the ARM processor has a whole load of additional functions on the processor, and the kernel has to support the actual processor. So we had to write specific kernel code. So we had to write a new kernel to support that particular processor so that we could actually use it. So that's how I know it was one of the first ones, because I had the code and had to patch the kernel to get it to... Yeah.
Thank you.